So for the first time now, we're going to evaluate limits algebraically. So last time I mentioned in math, specifically in calculus, there are always three ways to find the solution to something. And those three ways are graphically, numerically, which we did yesterday. Graphically is by looking at the graph. Numerically is like you just plug in points. And analytically. This is what we're going to do. Analytically is when you basically use like algebra-ish things. Okay, what is your question? We're starting with section 2. Here. Okay. Thank you. So let's talk about properties of limits. Okay. The first thing we're gonna build up with our functions, right? The first function we're going to take is the simplest function, which is y equals k. So when you have something written like this, right, that says the limit as x approaches c, whatever comes after that, that's the function. So if this is the limit as x approaches c of k, that means the function is y equals k. And so if you just take a look at y equals k, if this is the x-axis and the y-axis, if this is k, like k is 3, 5, 7, whatever, 2, y equals k is just a horizontal line that passes through y equals k. So if this is the value of c, so as x approaches c from the left-hand side and from the right-hand side, the y value is approaching k from both sides. Is that right? So if you just have a constant, then the limit as x approaches c of k is just k. For example, look at this one here. The limit as x approaches 2 of 3 is just 3. Okay? Because, again, what is that? This is just the line y equals 3. And if this is 2, as I approach x equals 2 from the left or the right, my y value is just approaching 3. That's it. Okay, so the next one is when your function is y equals x. Well, in a case like that, if I have y equals x, that's how that function looks, right? And suppose I'm approaching an x value of 3. As I approach x equals 3, what's the y value going to approach? 3, right? From both sides, it's just going to approach 3. So in that case, it's like this number just gets substituted into the x. Okay? Okay, so these are pretty much the building blocks. And then using these two, you can formulate any other type of function. So for the time being, I'm just going to ask for you guys to put away your calculators. And please, because we don't need them right now. I'm going to use these as building blocks to build all of our other functions. So let's talk about some properties of limits. All right? So suppose you have the f of x, and the limit of f of x is L. And then suppose you have another function g of x, and the limit of g of x as x approaches c is m. Then you can have all sorts of combinations. So if you add f of x and g of x, you just add the limits. If you subtract f of x and g of x, you subtract the limits. Multiply, same thing. If you multiply one function with a constant, you multiply the limit with it, and so on. Okay? So let's use that as an example here. All right. What is that first? Raise your hand, please. What is the first limit there? The limit as x approaches 2 of 3. Tyler, why don't you tell me? The limit as x approaches 2 of 3. It would just be 3. Okay? Okay, now here, the limit as x approaches root 2 of e, right? Root 2 of e. So e, again, is just a constant, right? So this will just be e. Okay? All right. So let's talk about polynomial functions. If p of x is a polynomial function, then if I want to find the limit as x approaches c of p of x, I simply just put c into x and find p of c, and that's it. All right, so we're going to use direct substitution for it. If you have a rational function, what's a rational function? It's just one function divided by another function. So again, you use direct substitution. Okay, so let's do a couple here. Take a look here. This is my function. I want to find the limit as x approaches 2 of that function. All I do is I take 2 and I substitute it into all of the x's here, right? So what I'm going to get there is 2 minus 3. And then 2 times 4 minus 2 minus 15, which will be negative 1 over negative 9. So this is 1, 9.
Wait, but couldn't you just,
Okay. So here, limit as x approaches to negative 1 of this function, we just substitute. So I get the square root of negative 1 plus 3, and that's just root 2. All right? Here, the square root of, the function is root x plus 6. We want to find the limit as x approaches negative 8. Now, if I put negative 8 in there, I get the square root of negative 8 plus 6, which is what? It's DNE. It's the square root of negative 2, which is not a real number. So what does that mean, right? What's the square root of x plus 6? When you graph that, this is what that looks like, right? This is negative 6. Now, this problem is asking you to find the limit as x approaches negative 8. Well, it doesn't. The graph doesn't even go there. So how do I know what y value it's approaching, right? That's just like barren country over there. All right? Yep. Okay.
well, that's x plus 6 or x minus 6?
A plus 6, but it still graphs that way. Okay, so the next one, we want this, the limit as x approaches a. A is just another constant. No big deal. Just put a instead of x, and we still get the same thing. Okay, that's it. Okay, this is all fine and well, but you know, things never stay that simple, right? So let's talk about indeterminate form. We had a rational function here. It was very, very possible for these to work out in such a way that you get 0 in the denominator, which is never a good thing. But more than that, it would have been very possible for you to get 0 divided by 0. So let me ask you something. What is 0 divided by 0? So the thing is, anything over 0 is undefined. Yes, absolutely. 5 over 0, undefined. 7 over 0, undefined. Negative 7 over 0, still undefined. 0 over 0, whole other situation. 0 over 0 is called indeterminate form because the function that gives you 0 over 0 can actually end up in more than one situation. A function that gives you indeterminate form, 0 over 0, needs to be simplified. So you have to use other methods to determine limits. And once you use other limits, there's plot twists here. It's possible that the limit might exist after all. It's possible that the limit might be negative infinity to positive infinity, okay? So we say either if the limit exists, we say it converges, or if it goes to negative or positive infinity, we say it diverges. So how do we deal with indeterminate form? Well, that depends on what kind of function you have. There are 3 different cases of functions. The first case is ones that require factoring. So take a look here. When I put negative 2 in here, I get negative 8 minus 12 minus plus 8 plus 12, which is 0, right? Over negative 2 plus 2. So this gives you 0 over 0, which is unfortunate. But it's indeterminate, so let's not be premature. So what you have to do then is you have to factor. Now, here's the thing. This numerator here is a cubic term that has 4 terms. When you have a situation like that, always try to see if you can factor by grouping. Okay, so we're going to factor this by grouping. Now, here is the thing. So let's talk about notation. Until now, when we were doing direct substitution, as soon as you plugged in the value, we drop that limit symbol, right? But here, I'm still finding a limit. I'm just changing up the expression. So here, I have to continue putting the limit symbol. So this is the limit as x approaches -2. When I factor this, I factor out an x squared and I get x minus 3. I factor out a -4, I get x minus 3. So this is equal to the limit as x approaches -2 of x squared minus 4, x minus 3 over this. So let's factor that further. Whoops. This is the limit as x approaches -2, x minus 2, x plus 2 over x minus 3, all over x plus 2, right? Do you see that? I'm just doing some algebra here. That's all I'm doing. There's no pre-calc here. This is just algebra. And at each step, this limit symbol has to come along with me. Otherwise, -1, okay? So this goes away, and as soon as the x plus 2 goes away, our problem is solved, because now we can no longer get a 0 in the denominator, and that's fine. So now I'm ready to plug in the x equals -2. As soon as I'm ready to plug in the x equals -2, I can no longer say limit. Okay? So now you know what? Let me just take another step and write it. So this is x minus 2, x minus 3. Now I plug it in and I get -2 minus 2, -2 minus 3. This is equal to 20. Okay. So look at this. Limit, 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 limit. No limit. If you put a limit here, another -1. Okay? This is very, very important. Yeah.
So you only put the limit when you're not plugging something in. Like
Yeah, as soon as you plug in the value, as soon as you start direct substitution, it disappears. So this one, we're going to get, we want to find the limit as x approaches 6 is 0 over 0 again. So let's go ahead and simplify. How does the top factor? Right. And then here, 3x plus 7, x minus 6. Okay, again, the whole x equals 6 situation went away. This is just the limit as x approaches 6. And I get 5 over 25, which is 1/5. Okay, so this is one way that we can solve indeterminate form. Okay, what if you have another situation? So here, this is the limit as x approaches 25 of that beautiful function. So 25 minus 25, you get 0 over 0, also indeterminate form. But now, there is no factoring to be done here, right? So what we're going to do instead is we have to rationalize the term here. Wherever the root is found, that's what you have to rationalize. It could be in the denominator or it could be in the numerator. So what do I multiply by to rationalize that? And you know what? I'm just going to do it here. Right. So here I'm going to do root x plus 5, root x plus 5. And you know what? I like to put parentheses around these to see what I'm doing. So this is going to be the limit as x approaches 25 of, okay, now pause what you're doing, everyone. Okay, because I know the type of students you all are, I know you all have this like fervent like desire to foil this, right? Do not foil this. Just copy it over. Do not foil this. Just copy it over. Okay? I know, right? Now this, you have to multiply this out. So it's a minus b, a plus b. You square the first term, you get x. You square the last term, you get 25. You have to put a minus in the middle. Okay, now what happens? It cancels. You see that? That wouldn't have happened had you FOILed the numerator. Okay? So now I get that this is the limit as x approaches 25, root x plus 5. And what does that give me? Just 10. So do you see that? In all of these cases, I got 0 over 0, but the limit is actually a cute little number for all of them. Okay, so how are we going to rationalize this one? How are we going to rationalize this one? So clearly this is 0 over 0, right? Because it's going to be 2 minus 2 over 0. What do we do to rationalize? 2 plus the root. 2 plus the root. So the limit as x approaches 0 of, you do have to multiply out the top. And for that, you square the first term. You square the second term and you get x plus 4 in parentheses. And you have to put a minus in between. This is the shortcut to foiling a plus b, a minus b. Is everybody okay with that?
Wait,
yeah.
So do you mind explaining that for us? You're saying you have to put the minus.
Okay, so when you have, okay, so whenever you have something like this, right?
Yeah.
Okay, you square the first term,
Right.
you square the second term, and then because there is a minus, you have to put a minus in between. So same thing there. Yep.
All right, wait, and then why? So for the one before you said not to multiply the numerator, but here you're
no.
multiplying it.
So okay, so what I'm saying is multiply out the one where you're rationalizing, but not the one that you're not rationalizing. So now let's take another step here. This is the limit as x approaches 0. So what's this going to be here? 4 minus x minus 4. What do you have left? Negative x on top, x on the bottom. Okay, so what now? The one that is being rationalized, that you multiply out, but not the other one. So the x's go away, and you're going to get the limit as x approaches 0, negative 1 over 2 plus root x plus 4. Now you can direct substitute. So you get negative 1 over 2 plus root 4, negative 1 over 4. Okay? Yep. Yep.
Wait, could you?
Oh, we also took x out of the bottom? It's wrong.
Otherwise, you'll still get 0 in the bottom. Yep. Okay? Okay, next one. Okay, all of these, we're looking for limits as x approaches a finite number, 0, negative 6, 2, 4, whatever. How about if you have to look for limits at infinity? Okay, limits at infinity. So here's what we're going to do. Okay, look. Okay, we're going to look at...
How did you get? So you got this x and y and multiplying with the numerator and the numbers.
No, there's an x times this.
Right, but how did you get this x and out of here these numbers?
Because you cancel it.
Oh, okay.
Okay, so take a look. If you have a power function, x to the n, what happens when x is infinity? Infinity to the power of n is infinity. Okay? Now, okay, what if you have negative infinity? Well, for negative infinity, you have to look at, is the function even or odd, right? If you're looking at negative infinity and you have x to the power of something, if this is even, you're always going to get positive infinity. If this is odd, you're always going to get negative infinity, right? So if you have the limit as x approaches negative infinity of x to the 4, that's positive infinity. But you have the limit as x approaches negative infinity of x cubed, that's negative infinity. Is that okay with everybody? Okay, so now let's talk about polynomial functions. Okay, let's talk about polynomial functions. You did this in Algebra 2 even like, and in the first semester when we did end behavior. You guys remember that? When you do end behavior, that's the same as evaluating a limit at infinity. That's just end behavior. End behavior is like the rudimentary term for a limit at infinity. When we did end behavior, what did we do? When we had a polynomial function like this, remember you only took the term with the highest degree. Do you remember that? So now this is 4x to the 6th. So as x approaches positive infinity, this is just going to approach positive infinity. In the next case, the term with the highest degree is negative infinity, negative x cubed. And if you're looking at x approaching negative infinity, it's going to go to, so this is negative, right? There's a negative out here. Now, if x is also a negative number, the negative cubed will be negative times another negative here, it'll be positive. Okay? Yeah. So you have negative x cubed, right? So let's just say, okay, now this is going to be negative. The x cubed is negative x, right? So negative x cubed is going to be negative plus another negative out here. So it's like if you have negative x cubed.
Oh, the negatives
Okay.
are outside.
Now, yeah, make that red x a negative number. Cubed, it's still a negative number. Now add the outer negative, it'll become positive. Okay? Yeah.
Does that watch? No, it won't get.
Okay. So here, what's the highest degree here?
4x to the fifth.
It's 4x to the 5th. And as I'm approaching negative infinity, what will that be?
Negative, yeah.
Negative infinity. Okay, here I have minus x squared, but it's going to positive infinity, so this will also be negative infinity. Okay? All right. Now let's take a look at reciprocal functions at infinity. So remember, reciprocal functions look like this, right? It's basically, this is the graph of 1 over x, right? So when you have 1 over x, can x ever be 0? No, so there's a vertical asymptote. Okay, if x is positive, y is positive. If x is negative, y is negative. What value of x makes, what value of x makes this 0? Is there a value of x that makes this 0? No. So that's how that looks. Okay, so now, as you approach infinity then, do you see how this levels off to y equals 0? Yeah. Okay, so now, so let's take a look at this for a minute. I'll take your question in a sec. This is the limit as x approaches infinity of 1 over x. So now, this concept, right, of these reciprocal functions, I can't tell you how important it is for you to be able to visualize it. If you have 1 over x, and if that denominator gets infinitely large, what happens to the entire value? It gets smaller and smaller to 0. So that's why that's going to be 0. Now, if I have 1 over x, and that denominator is a positive large number, like positive trillion, this is still going to be 0, right? But if it was negative a trillion, what would the whole thing be? Also 0, but from the, right? So it'll still be 0. Okay, so, all right, so let's talk about rational functions at infinity. So this was if you just have 1 over something. But what if you have a function over another function? Okay.
Sorry.
Okay, so what if you have a polynomial function? Same thing as we've done before. Compare the degree of the numerator to the degree of the denominator.
Can I go outside, please?
Yep. You okay?
Yeah.
So many things happening today.
Bless you.
Okay. Okay. So, okay. This is how we always found horizontal asymptotes, but let's just talk about the limit at infinity. What we're talking about, if you have a rational function, where does the y value go as you approach infinity? So, if the numerator has a lower degree than the denominator, then the limit as x approaches infinity is 0. All right? So, for example, take a look at this one. What we do for these, again, take the leading term from the top, the leading term from the bottom. This will reduce to limit as x approaches infinity, x squared over x. This is the limit as x approaches infinity, 1 over x. And now this is clearly 0, right? 1 over an infinitely large number is going to be 0. Okay? Huh?
Why is it x squared over?
Because it's x cubed. Okay, so here, what if the denominator and the numerator have an equal degree? Take the highest term from the top, the leading term from the top, the leading term from the bottom. Limit as x approaches negative infinity, negative 2x cubed over 6x cubed. These go away. So we just have the limit as x approaches negative infinity of negative 1/3. And what did we say in the beginning of this lesson? When you have the limit of a constant, what's the limit? It's just the constant, negative 1 over 3. Okay? And then, if the numerator has a higher degree, so let's see this one. The limit as x approaches infinity. Leading term, leading term. This will give you negative x squared. So, we're looking for the actual limit here, not an asymptote. So the limit here will be what? Negative infinity. You okay?
Yeah.
Okay. So if this gets infinitely large, this whole thing will be negative infinity. Okay? So you can say negative infinity, or you can say dne, but negative infinity. Either this or these two together. Okay? All right. Questions? Yep.
I don't understand the DME like negative infinity.
So, what